Okay, so on that note, on that note, for the end of class, it is eval, so it's probably, like John Paul mentioned, a really bad idea of me to frustrate anyone right before eval time.
Not a good time.
But the way that I teach, I run my classrooms, is very much based off of data that I collect. And student perception of performance is one, student actual performance is another. So that survey, the post-survey that I have you guys take, I correlate that to something similar you did in the beginning of the semester, and I look at what gains students have made over the course of the semester to see if I need to change things, if there's things I need to improve. So both of these pieces of data are very important to me. One is the student evals, which the department will get and look at. The second is that post-survey, which is why I incentivize you doing it with extra credit that will go towards your mastering grade. So there are 3 extra credit pieces that go towards your mastering grade. The post-survey I just talked about, the learning assistance survey, and the pre-survey that you did at the beginning of the semester. If you notice, I have not been able to figure out how to give you extra credit for that yet, so I will do that on the back end. So those 3 things will go to boost your grade in mastering.
How index your credit?
It'll be worth a full, I can't remember, I haven't decided if I'm going to do it in post-quiz or homework, but it'll be worth a full one of those, either one. They're all worth the same.
That was that email you sent. It has the link and that's everything we need.
The 2 links are there, yes. And that is what you need. All right, so the other announcements, besides your extra credit opportunities, in order to get the data that I would really like, the LA survey is just to make sure that we get feedback on the learning assistance that we have had in the workshop sessions and try to convince the university that it's worth the money that they spend in order to bring those sessions to life. Sometimes your grades don't get uploaded accurately. It happens, we're humans, and we do transfer of numbers from one place to the other. So always check all of your numbers to make sure that you are assigned the grade that you earned. What that means is check your workshop grade. If you don't know how to do that, go into Blackboard under My Organizations, you'll find your grade there. Check to make sure that was put properly into your Blackboard lab site. Make sure that your Blackboard weighted grade is the grade that I end up putting into your final lab grade in Blackboard course site. Make sure that all your exams are up to date. Make sure your clickers, your mastering homework matches across wherever you can find the data. That responsibility is on you. I will do my utmost best to make sure it's accurate, but I miss things, and so you bring them up to me as a way to make sure it's more accurate than it could be otherwise. End of class today, I'll give you guys 10 minutes to fill out the student evaluations on the bubble sheet. The only thing you will put on there is the student ID is going to be the number that's shown on either side of the board here. That will identify it to be this section of our course. Any quick questions?
Do we get extra credit if we make sure these surveys are good?
Since I have no way of knowing if they're good, then the answer is unfortunately no.
I mean, just power numbers, so it's really good.
I hope that you are fair and honest with your evaluation of me, John Paul. Okay. So today's class, many of you will be working in the field of medicine, so I wanted to spend a little bit of time talking about nuclear medicine, because that is a component of the medical field. Hopefully you all completed the pre-class primer, which was watching that 4-minute YouTube video. If you haven't, watch that when you go home before the final exam, because there will be a question from the final exam that comes from that and today's material. Maybe 2. All right, so take a look at the reaction that's shown here. I want you to determine whether you think that this is a chemical reaction, a nuclear reaction, or if you're not sure how to determine that. Last time you have to log into clickers for this class. Once you've clicked in your response, feel free to ask the person next to you. Okay, we have 34 responses. Is that about everybody that's here today? Seems like we got maybe 45. Okay, we're up to 39. So, how do we look at this and try to figure out what type of reaction it is? Who wants to share what insight they might have? Kisa?
It's a transfer of
Nice and loud so everyone in the back can hear you.
transfer of neutrons.
Transfer of neutrons. What do you mean?
So like that, the top numbers on the RA goes from 226 to 222 and a 4
What do we call that top number?
neutrons. Oh man, I might be wrong.
What's this number at the top? Mass number.
That's right.
Mass number is what?
Protons and neutrons.
The total number of protons and neutrons. Part of today's class is going to be review. We're going to use nuclear to hit some review topics, okay? This is like week 1. So it's been a while, I understand that, but it's going to be really important that you leave this class knowing what an element is, what identifies it, different isotopes, all these kinds of things. So we're going to spend some time on that. So Kisa picked out that we start with radon 226. We end with radon 222. Is that a chemical reaction? No. What does not change in a chemical reaction? Protons and neutrons. So any atom that you have before, you have after the reaction. Conservation of mass and conservation of really atoms. But one of the things we haven't talked about is we've said, well, radon would always stay radon, but that's not the case. When you have a nuclear reaction, the nucleus of the actual element itself either breaks apart, gains things, number of different things, but you have a change in the number of protons or neutrons. If we change the number of electrons, is that a nuclear reaction?
No.
So Chris is very certain no. Why?
Because if you're only changing the electrons, it only has to do like with the electron shells, right? And thus you're not actually changing the nucleus that's inside.
So the nuclear reaction, just pretty straightforward once you kind of catch on. Nucleus, if it changes the nucleus, it's nuclear reaction. If it doesn't change the nucleus, it's not a nuclear reaction. So if it changes the number of electrons, that's outside the nucleus, right? Those electrons are in clouds around it. And so specifically, if we transfer electrons, we call that a redox reaction. All right. So I agree, we change the nuclear components. If the mass number changes from before to after, that's one way to tell, the easiest way to tell. Does anything else? Ooh. And there's actually a mistake on here. Can anyone pick out what the mistake is? Talk to your neighbor. What's the mistake I made on in this reaction? This would be a great exam question. What mistake is in this reaction? I love this.
I'll cry.
Got a new question coming.
What? The exam's not made?
It is, but it can always be changed.
Like it's not hard enough for us to get the right stuff.
Okay, a new voice. Who has noticed what I did wrong in this reaction? Can I get a volunteer? What's wrong? New voice. Donald.
Is it that there's 86 protons instead of 88?
Okay, so after the reaction, we have a different number of protons. That's what it's supposed to be. So what's the mistake then? It's related to that.
That it didn't change to whatever he is. 86. RN.
So we started out as radon. We lost how many protons? 2. So it should be... I actually have no idea what RN is. Someone can look that up while we're going forward. And they gave me a PhD.
RN is radon.
So what is RA?
Is it radium?
Radium to radon. That sounds right.
Radian?
Yeah, it is radium. Radium is
Radium.
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 What would you use with
The one that Marie Curie found.
It's a noble gas.
So we're changing from one element to the other. What identifies it as the element is the number of protons that it has, and I changed the number of protons and said it was still the same element. So that means that that was a big mistake.
Was it supposed to still be an RA?
So we do still have conservation of mass. So nuclear reactions do still completely conserve mass. So we start out with 226 particles that have mass, right? Protons and neutrons. We end with 222 here, and there's 4 more. So we still have the same total number of protons and neutrons. 88 protons to 86 protons, and there's 2 over here. So do you know what type of chemical reaction, or nuclear reaction this is? This is called an alpha particle, a helium atom. So this is alpha decay. Shelby?
Yeah. Or is radium and then iron is radium.
That's the second.
That makes sense. That looks good. It's a good thing I'm not recording this. Will forever be in my history. Okay, so let's use that then to bounce towards some kind of reflective discussions. So I agree this is a nuclear reaction. So by the end of today's class, I want you to be able to look at a reaction and determine whether it's a chemical reaction or a nuclear reaction. And then I want you to be able to, part of it was in the video, we're going to talk a little bit about it in class today, is to discuss what the relative danger is of different types of radiation. And then let's do a little bit of review. So on your paper, question number 2, I want you to look at each one of those, determine how many protons, neutrons, and electrons each one of those has. We're going to start off with niobium, which is 2A. Go ahead and figure out for all of these. Click in your answers. So as you figure them out, go ahead and click in the number of protons.
I was going down to the next. Because it's easier.
We're up to 33 responses for the number of protons. So once you've submitted your response, keep working, but make sure you submit your first response, please. All right, we got 39. Okay, I'm going to go ahead and close this out. So who wants to describe how we found this? Should we go through all 3 of them first, maybe? Would that be better? Let's do that. So go ahead and click in the number of neutrons. All right, need 10 more responses. We do have our team in here, so if you're getting stuck on any of these, like one of us down. A couple more seconds to put this in.
So, a lot of times, like,
Keep going.
I've explained
All right, closing out.
methodology, right, is to relate people, right? And so, because the police
All right, and the last one, go ahead and click in how many electrons we have in this atom.
it creates like, because if you look at it like this, where like, let's see, this is your head, right? And then your hair is like this like this. If your hair is like up here, it's like this.
All right, we're at 31. A couple more responses.
So, oftentimes, you don't know how many electrons. I mean, it's a neutral, so protons are positive. So,
Closing out.
same number.
Okay, so let's go through these. Can I have one volunteer, new voice, who hasn't talked yet today, to talk through those three numbers? The class is pretty much in agreement, so we don't need to spend a whole lot of time going through this. Alexis, would you like to talk through these three numbers and how you determine them?
So, for the 41.
So the atomic number at the bottom tells you how many protons it is. If we look in the periodic table, 41 is niobium. Great.
And then electrons is also 41 because there's no charge.
Great. So it means we have the same number of both, positive and negative.
And for the neutrons, I minus the atomic weight of the atomic number.
So we're going to take away from the mass number
Mass number.
the atomic number. So the number of total protons and neutrons minus the protons gives us the number of neutrons. What would you find for that? 52. Great. Any questions on how we found those values? So then, what's the full electron configuration? So I'm not going to do this as a clicker because I think it might be really difficult to read and to enter. So why don't you go ahead and write out the full electron configuration on your paper? We'll come by and take a look at it.
That's the squares, right? The numbers.
Starts with
Like the,
1s2
yeah, that.
and then keeps going. All right, how are we feeling about this one? Is this something that we need to refresh? Like, AKA, you go back and study?
I just felt there was
Okay. So can I get a new volunteer to read off the full electron configuration? You have a question first? So I already have on the exam one of those little ladder things that you're going to have to fill in, but you can use that in whatever context you want. Yeah. So who wants to talk through this one? Who wants to talk us, or basically list off what the orbitals are and electrons in them? Go, Sam.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
Okay, and pause for 1 second there. So this is where I think a lot of people are getting confused. Where does 3D come compared to 4? Is that right? So remember when we're looking at the periodic table, what do we call the block over here on the left side? S block. What's this block in the middle? D block. P block. So I don't even remember what comes before what, but I just say, okay, as I go across the top, we have 1s1, 1s2, 2s1, 2s2, 2p1 through 2p6. And you just keep going, and there's no D here. So we know that D starts at 3, but it's shifted down 1. So that's how I remember it's 3s, 3p, 4s, 3d. Is that, just looking at the periodic table, that's one of the ways I want you to be able to use it. Okay, Sam, continue.
4p6, 5s2, and 4d3.
4d what?
3.
Okay. So we finish with the S block with 2 electrons. It's the 5th group, period. 5th period. And then we get into 4D, 1, 2, 3. I concur. But we don't like writing the full configuration, right? It's way easier to write the noble gas electron configuration.
That's right.
So what is the noble gas electron configuration for this? Which of these can we say are noble gas configurations? We can summarize with just a square bracket and a symbol. Carmen? Say again?
I'm probably saying the wrong.
Yep, so what's the configuration for that? Where does that, do you want to bracket it? Go ahead and write the brackets where you think krypton's configuration is. What do y'all think? Does that look reasonable? Okay, so we can replace all of that and just say KR, and then we just have to use the rest, 5s2, 4d3. That's the noble gas or the condensed configuration. They say exactly the same thing. So what are some ions we'd expect to find of niobium if we found it as an ion? Talk to your neighbor. What ions would we expect to find if we found niobium as an ion based on its electron configuration? Don't all talk at the same time.
Can you repeat the question one more time?
If we go out in nature and find that niobium is actually an ion, in this case it's not. This is not an ion, right? This is neutral. So we know it had 41 electrons. But if we did find it as an ion, what ion would we be likely to find it as? Talk to your neighbors, look at the electron configuration, and try to come up with an argument.
Because it needs to.
And do not use this stupid...
Oh, come on.
Do not use
I
that.
love it so much. No, don't actually do that. How did you make
I was
Well, you have just blown her mind. Did you hear that?
Listen,
It would be
that was
more
the
like
sound of your evaluation.
Okay, so let's think about the logic behind it. Shelby, do you want to talk us through it?
It would be closer to building. So it would lose 5 electrons
So if we lost 5 electrons So we're either going to lose or gain electrons to get closer to noble gas configuration, a more stable configuration. If we lose, let me change colors. If we lost these 5 electrons, we would have a noble gas electron configuration. So that would give us Nb plus 5. So we're always looking, what's the nearest noble gas configuration? That's one of the reasons that I want you to be able to write the noble gas configuration, is because then you can say, oh, it only has 5 more electrons than noble gas configuration. It's either going to gain electrons to be more like the next noble gas, that's a lot of electrons, or it's going to lose electrons to be more like this noble gas. And that's not the only way it can lose electrons. It can also lose other electrons, but it is a metal, transition metal, so that means it's most likely to be a cation or a positively charged ion. And if it's going to lose some, our first guess is it'll lose enough to be an electron configuration like the previous noble gas. What's the electron configuration for niobium 5+? Does that look good? This electron configuration is the same as krypton. So these are all kind of refreshers. If any parts of this are like, ooh, I need to go back and study that, now make that note, and then come to one of the many study sessions in the next couple days. Okay? Let's answer this just so I know where everyone stands. Couple more seconds. Almost done. All right, gonna go ahead and close it up. So a vast majority are agreeing that the number of protons defines the element. If they have different neutrons, are those different elements? What do we call those? Isotopes of the same element will have the same number of protons but different number of neutrons. What if they have different numbers of electrons but the same number of protons? Those are ions of each other, potentially. Yeah, I feel like that's reasonable. So instead of going through and doing each step individually, how about go ahead and do the 3 protons, neutrons, electrons for this symbol, and then we'll call those out. And I think most people have been working on this, so let's take just about 45 seconds, if you have not already, to look at the symbol, determine protons, neutrons, and electrons.
Did you change it over on your end, on our end?
It's not a clicker question.
Oh, okay.
It will take too long to do all 3. So.
Negative means it's gain. 3 negative means it's gain.
Oh, that's an L, isn't it?
Feeling ready? All right, new voice, new volunteer. And I'm going to call on someone, and I just want to hear your answer, and then we can build from there. So, Dustin, would you like to talk us through the 3 components for arsenic?
Yes, because I have the question. So, for the protons, I got 33. I had a question about the neutrons, though, so I didn't answer that one.
Okay, and
For electrons, I got 36.
did anyone answer this? What did you all answer?
42.
This is the correct answer. Why?
Oh, because the mass number is not the atomic mass.
We don't have a mass number. We don't know what isotope it is. This is saying all average for this molecule. There's multiple different isotopes, each one that has different number of neutrons. So this is ambiguous as to which isotope. Actually, it specifies it's the natural abundance of all of them. So there is no individual isotope. So you could say, well, one of them could be, then you could give a specific number of neutrons. But this is a correct answer. Okay? Questions on that? So let's go ahead and jump through to our next one. Let's do the same thing for our titanium species. Go ahead and determine protons, neutrons, and electrons. And then I'll ask for a volunteer to talk through that as well.
No, it's not. It just says.
All right, are we ready to talk through this one? We need another little bit. Ready? Okay. Can I hear from Jocelyn for this species? What did you have for number of protons, neutrons, and electrons? Okay, so you got 22 by looking at the atomic number of titanium, because that defines titanium. So we either need one or the other. Sometimes you'll see both, right? On some of these earlier problems, I gave you both the atomic number and the symbol, but they mean the same thing. The difference between 22 and 50 is the number of neutrons, so that's 28. And then you said that there's 2 fewer electrons than protons, so that gives us 20 electrons. Great. I don't think I have the electron configuration for that one, but I think we will do electron configuration for our last one. So go ahead for our sulfur species. I want you to determine protons, neutrons, electrons, and electron configuration. Let's do condensed electron configuration to save us some time, though.
What did you get? I got 3. Oh, yeah, I didn't get that. So, yeah. That thing helped you. I saw it. Yeah. Yeah, everything. I just got a better picture of that. This one looked like this.
No, I used to do a lot of boxing back in high school, and eventually, I was a coach.
Wait, which one were you supposed to be doing? The S and N or the T? We're doing the S one? Are you taking that one?
All right. Monica, thank you for volunteering for this one. Can you tell us the number of protons, neutrons, electrons, and then, once we have those, the condensed electron configuration?
Okay. Protons, I got 16 for the atomic.
Great. 16 is the atomic number. Fantastic.
And then for the neutrons, I subtracted the atomic mass. Well, I subtracted the 16 from the atomic mass.
Atomic number, or from the mass number.
From the mass number.
And you got?
17.
Okay. And how many electrons did you get?
And then because it's got a negative 2 charge, I added 2 to get 18.
So the negative 2 charge, I like how you said that. We know that if it was neutral, it would have the same number of protons and electrons. It has 2 more of the negatively charged particles, so that means it has 18 electrons. So now, what is the condensed electron configuration? You want to go for that one too, Monica?
Okay. So, what is NE?
Neon?
Neon. Okay, so neon, since it already got 10 here, I used it, and then I only had to get to 16, so I only needed 6 more.
So where do those go?
Where do they go?
What shells are they?
Oh,
Subshells. You want to phone a friend?
3, okay.
Are you good?
Yeah, I want to call it first.
Okay. Olivia?
Oh, you're just assuming I'm her friend? 3s2 and 3p4.
Great. Are we happy with that?
No.
Uh-oh. What did we miss?
It's 18.
Oh, crap.
How many electrons are in here? This is 16 electrons. This is a bright electron configuration for sulfur, not for S2 minus.
So what it needs to be?
So we're right. We're good now, right?
Yes.
Nope. What is the final answer for this?
Oh, man, look at that.
Why did sulfur gain 2 electrons?
I did that whole thing.
So careful with our wording. It's not so it will become argon.
Be light.
It's so it will have the electron configuration of argon, which is a more stable electron configuration because it's a full octet. Okay?
So putting neon 3s2, 3p6 would be incorrect on the exam?
You'd want to
True.
put AR
You
on
didn't have to
the
put
thing.
that X right there.
This is a correct number of electrons, but if we're doing a condensed configuration, we say, what is the simplified version of this? And this is not the simplified version. This is the simplified version.
What?
The most simplified version of S2 minus is argon squared brackets electron configuration. Okay, so let's go way back, and now that we are totally comfortable with what, let's do one more question that I actually don't have on your sheet.
I saw the valence.
Quick question.
So if that wasn't argon and that was the simplest, would that be right?
Sorry?
Like if it didn't add up to the argon and that was the simplest.
So if it was sulfur 1 minus,
Right.
then it would be 3s2, 3p5. So you don't write the condensed configuration as a noble gas unless it is the configuration of the noble gas. Good question. Okay, so what I want to do is I want you to choose one of these answers. So we're looking at BBs, these little pellets, and sometimes they're made out of lead. So how many individual atoms of lead are in a BB that is made of lead? And I have a visual there so you can see how big they are. I will give you until 1 minute 30 to select your answer.
How much is in a BB? What? Wait, what are the dimensions of the BB?
Like this,
What?
all the way around.
I can't quantify that.
Try thinking about what you know and how to answer this question. You have enough information to answer. All right, a couple more seconds. Without fail, there's always one answer that prevails in this type of question. Why?
Because we know that, right?
Because we know that number. Does that mean it's a right answer for any question?
It says Adam.
No.
But it's a big number, and you know it should be a big
Okay, so let's think about the logic. What do we know?
I don't know.
There's a lot of
It mentioned
atoms.
atoms.
I live in uncertainty.
I know lead is a P.
Okay, so we know lead is pretty heavy. How heavy? Can we specify?
200 grams per mole, I think.
Fantastic. So lead weighs 207 grams for 1 mole. Why is that number relevant?
Because that's 6.2.
Because answer D is a mole. So if we had a mole of it, one of those BBs would weigh 207 grams. Does that sound reasonable? You've been in lab all semester. It's not like I'm talking about a unit you've never seen or played with in person, right? Like you've gone to lab. Have you actually been the person who weighs something? Because if you have, you would know that 200 grams, it's pretty heavy. You probably need a block like this big of lead to have it be 200 grams. Something pretty sizable. So then, is it going to be more or less than 207 grams for one of these BBs? It's going to have to be less. Is it this much less? 1,000 atoms? That's really, really, really small, right? Is this answer possible?
No.
Why not?
Because it's the negative.
We didn't see it.
This is a fraction of an atom. That doesn't exist, right? You can't have a fraction of an atom because that's not an atom anymore. So only one of these answers makes logical sense. So congrats to the 5 people that answered that question correctly.
My life is uncertainty.
Okay, so take home from that problem is I want you to leave this class with some semblance of scale. How big is an atom? How small is an atom? How many atoms are in the concrete made to make this building? If you say it's a mole, I'll cry. If you say it's the same as the number of atoms that are in a calculator, as the number of moles, number of atoms in the whole building, right? There's some scale. So I want you thinking about how big and how small things are. That's the point of a question like this. And there will be a question like this on the exam. Something where I need you to approximate size, even though you don't know the exact weight. It's not a conversion. It's a conceptual question.
Is that like the actual number though?
I'm not going to give you that question on the exam. Is that what you... No.
No, I mean, like, was that like the
So
actual
it was
number?
less than a mole.
I have no idea. I made up the number, but it's about 100th of a mole. Maybe 2 grams is how much one of those BB weighs. It seems reasonable. Okay, so let's do a couple more. Let's do these 2 questions. Are these chemical, nuclear, or we're still not sure about the type of reaction? Couple more seconds. Closing out.
No.
Okay. So, majority of the class says that this is a chemical reaction. Why?
I don't know.
looks like double displacement, maybe.
Is that, no, that's
It's redox, right?
Single, it's not actually a displacement reaction, it's a redox reaction. So we have change in number of electrons. This goes from uncharged to charged. This goes from charged to uncharged. We're transferring electrons. The identity of any of those elements doesn't change from the beginning to the end. Right? In order to be a nuclear reaction, you have to change the number of protons or neutrons in an element, left to right. All right, what about our last one here? This is a question. We're getting really far today. We're on 3B. 45 minutes in the class. Do you want to answer or do you have a question?
Okay, so, on the test, are you just gonna include the stuff that you've learned since the last test into the final, or are you gonna put it at the beginning? Okay, and also, so what happens to the reaction? Is it gonna be now nuclear,
It's a good idea. I haven't done that in my questions so far. Okay, a couple more seconds. All right, there is a discrepancy. You all do not agree with each other. Convince someone you're right. 20 seconds. Convince them you're right. Come on.
It doesn't change the nucleus.
Same answer.
You guys don't know anything about
Information.
What did you guys put? Yeah.
Completely unquantified.
I had nuclear not change the
I mean, you could be like, a victim of a horrible war accident and lose half your mass.
All right, go ahead and make sure your answer that you have now is your final answer.
I'll go back to my first answer. I'll go back.
And we're closing out.
Oh, I regret it.
Oh man, I feel like losing like half your answers.
So we're feeling pretty good about this, huh?
I appreciate that one person that was honest.
Yeah, I think probably a lot more people should have been here if they were honest with themselves based on this. How do we choose? Bradley, how do we choose? Okay. Anyone have a answer that they want to share?
Alright, I'm not sure. If I'm being honest, I probably should pick C, but my mindset on choosing A was that a chemical reaction does transfer electrons, where a nuclear reaction deals with the nucleus and the protons and the neutrons are in the nucleus, but this one doesn't deal with the protons or the neutrons, it only moves the electrons, so I'm thinking it's chemical.
What do y'all think?
I think she explained it really well. I think that sounds good, right? Yeah.
I agree. There is no change to the nucleus, so it is not a nuclear reaction. That's our simple rule, right? Nucleus stays with 6 protons, 6 neutrons. Charge changes, it kicks out an electron, but that's a redox reaction, not a chemical reaction. Okay, so let's talk about nuclear reactions. Why do we care about them? They're used in energy and they're used in medicine. So in energy, it only takes about 50 kilograms, that's less than my body weight, of nuclear fuel to power enough electricity for 1 million people. I think that's for a year. There is 0 air pollution. Is that completely true?
No.
That's if things go right. Has anyone seen the Chernobyl show on HBO? Incredible. You should watch it. Super cool. Super accurate historically, a lot of it.
I watched the ones with
Physically, very accurate. Super cool. Check it out. So, what other alternatives do we have? How else do we get energy in this country for the most part? Coal. So, is coal, do you think 50 kilograms of coal will get us enough energy for the country for a year? For a million people?
It has a huge carbon footprint.
So it takes about 2 million kilograms of coal to get us the same amount of energy as 50 kilograms of nuclear material. In addition, when you burn coal, it reacts with nitrogen in the air and sulfur that's in the coal, and you get noxious gases and SOx gases. These are things that when they combine with rain or clouds generate acid rain. So it generates nitric acid and sulfuric acid in the rain. Also puts out a lot of CO2, greenhouse gases that warm up our planet. So why don't we just use nuclear energy?
Nuclear waste.
So at the end of using that 50 kilograms, we still have 50 kilograms, but now it's radioactive, not radioactive enough to use as fuel. What do we do with it? So we bury it until we figure out, some smart people in the future figure out what to do with it. Yeah, put it in the ocean. That's, yeah.
Put it into space and let someone else
So there's a lot of environmental concerns once the material is spent, or, heaven forbid, there's actually an accident while we're using it. So Chernobyl is a great example of that, where there's no one that's lived there for 70 years now, and they don't think anyone's going to be able to live there for, well, they have a dome on it now so you can get closer, but that fuel will not stop emitting nuclear radiation for, I think it's like 1 million years, something along that timeline. It's a very, very long time. Humans will probably not be around by the time it stops being radioactive.
Is that where all the dogs are?
Yeah.
There's probably a lot of dogs there,
There's a lot of
and that
dogs
show,
over there.
that Chernobyl show talks about how they tried to eliminate all the wildlife and it didn't work. It's very interesting. So I have a set of statements here that are either about nuclear or about chemical reactions. Go down, and for each pair, right beside it, so there's two like A and B. One of those is chemical, one of them is nuclear. So pick C or N for those two. Go to the next one. Pick C or N, decide which one goes where, and kind of go down the list. Take about 2-3 minutes to read through each pair. Each pair is one C and one N. So I'm going to go through each pair and have you click in your responses for which is which. So go ahead and click in which order it is for the first pair of questions. All right, let's go ahead and walk through these. So the first one has 39 responses. Overwhelming majority of people say that this is the first response is chemical, then nuclear. So one substance is converted to another, but atoms never change identity. Remember, if the protons don't change, then that cannot be a nuclear reaction. So I agree with the majority of the class. Let's look at our second two. Go ahead and click in which order you think this is. Couple more seconds. Closing out. All right. Once again, majority of the class agrees. So the top one, orbital electrons rarely take part. I think it's what's supposed to be, not place. So for changing neutrons and other particles, and that's going to be nuclear for sure. And then the one that focuses on electrons changing partners is going to be a chemical reaction. Third pair. This is one of the big concerns. and benefits of nuclear versus chemical. I'm not quite sure about this one. Check with someone next to you if they have a... Try to find someone with a different answer.
We need to find someone who doesn't
All right, we're closing out.
Taylor's feeling icy over here.
It's the caffeine. The amount of caffeine I have,
All right, so here is the crazy part of nuclear reactions. If you think about a nucleus, you have protons and neutrons. They're neutrally charged neutrons, right? Positively charged protons, and they're all being held together. They should repel each other. And so there are these crazy forces that we talk about their binding energy. How much energy is actually required to hold them together? And when you disrupt those atoms being held together, that binding energy is released. And so, I don't know if you remember, we talked about the mass of all these isotopes. And we talked about the isotopes don't weigh exactly the amount that we think they should. If you have 16 mass particles, they don't weigh exactly 16.000 AMU. It weighs a little bit less. So this is where Einstein comes into play. Have you heard of this equation? That binding energy is the mass defect. That's why it doesn't weigh 16.000 AMU if you have 8 protons and 8 neutrons. So this relationship describes some of that. And so when you change the binding of the nuclear components, you get huge changes of energy. Nuclear bomb, right? Something that could fit on this desk right here can take out millions of people in a city. That's how much energy is released from these nuclear reactions. So we have to be really careful with nuclear reactions. And the changes in mass are related to this formula here, where that energy comes from. Chemical reactions, you measure the exact same mass before and afterwards. All right, last pairing. I think so. Yes, A sounds right.
Yes, it sounds good.
All right, closing up. All right. Interesting.
Bam.
Not quite sure why everyone got 100% on this one. Maybe from the video or stuff you've done.
You got it.
You should be proud.
Didn't teach it all.
That's the first time
Good job.
Got a whole
All right.
explanation right.
We only have no, I don't need to explain that. You guys are good. We only have 6 minutes left until I need to put out the surveys. So let's talk about the main different types of radioactive decay. You put some radioactive material here. Maybe it's uranium, maybe it's something else. And you shield most of the radiation coming out of it. There's 3 main types of radiation that you should be aware of. Those main types are alpha, beta, and gamma radiation. So based off of those 3, I want you to answer question 11 and 12.
Can we also go through 9?
Oh. That's where I was looking. I didn't see it. Okay, so questions 8, 9, and 10, you should be able to answer based off of this diagram. So if we're having this radioactive material emit radiation, it's passing through 2 charged plates, electrically charged. One is negatively charged, one is positively charged. And then we're seeing where they end up after they go through that. So based off of what you see here, I want you to determine which is a positively charged particle, which is negative, and which does not have a charge. So do we have a good idea? Can I hear from Rakaya? What did you and Jamie say for the charges of the three particles?
So for A, I said it was beta.
Beta is, what is it? Positive, negative?
Charge, positive.
Okay, so you said that this one is positively charged? Do we agree with that? So if it's positively charged, is it going to be attracted to or repelled from the positively charged plate?
We did that.
So a beta particle is negatively charged. Something crazy? Beta particle, it's an electron. It's an electron, but it's not just an electron coming off of the outer clouds. It's actually a neutron that breaks down into a proton and electron. Okay, if you want to learn more about this, it's super cool. All right, what's the charge then of an alpha particle? Why is it positive? Okay, and gamma rays? It's not attracted to the negative or positive, goes right down the middle, neutral. Gamma rays are actually light. It's a form of really high energy light, and there can be different wavelengths of light that's emitted from nuclear reactions. Gamma rays are some of the most dangerous, but when they run into DNA or other things that absorb light in our body, they actually will change the structure of DNA, and then when you replicate cells, you get cancer. So that's one of the main ways that it can be very dangerous. So then the second part is, what's the relative weight of these? Which one of these do you think is heaviest? Which one is lightest?
I think alpha. Beta. No, alpha.
Which one's heaviest?
Alpha.
Why is alpha heaviest?
Protons are heavier than electrons.
Okay, so we know that protons are heavier than electrons, but let's look at where they go in the field too. If this is going straight through, they both have the same charge they're fighting against. And this one just bends a little bit. It's because it's a lot heavier. The same force doesn't bend it as far. Versus the beta particle, same force, bends it a lot further. It means it has less weight. Goes outside. What about light? Does light have any mass? Very, 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 so small we're going to say it has no mass because it's E equals mc squared is the relationship between that, and we're not getting into that. So then if we think about their ability to permeate through material, or to penetrate into, if you think about that, if you're standing in front of one of these types of radiation, think about which one is going to be able to penetrate the furthest into your body versus the least far into your body. So do you think alpha particles penetrate the most? Beta or gamma? Which one's the second? Which one's the least? This is a clicker. It is also question number 12. Sarah and Akia, can I get you all to help? You just pick alternating rows. Couple more seconds. And don't, if you can put these face down. Sarah and Akia. Yeah, so let's not start with evaluations yet. We're just trying to get them out to you so that after this question we can start working on it. All right, we have 40 responses, and we're kind of all over the place. Anyone want to explain what and why? Should we look at a visual first, or you want to explain why first?
Visual.
So you have a tank full of water, and there's a little bit of air at the top. And if you have the three different types of radiation, which one goes the deepest and why? Gamma goes the deepest because it's the lightest. Beta particle does penetrate, not as far, and alpha particles barely penetrate at all. If you think about trying to force something with 2 protons and 2 neutrons through your skin, it's not going to get very far. So you can literally just wear a doctor's gown, and it protects you from alpha particles. Beta particles, you might want to have lead on, because then it doesn't penetrate at all, even through the surface of your skin. In gamma rays, you need a lot of lead to keep that from going through.
Why lead? Like,
So,
that property?
lead is a very interesting substance because the nuclei are packed so closely together that a lot of the radiation actually hits that and interacts with the lead instead of going through. So, there was one last thought I had on this. Oh. How does radiation actually damage us?
It changes our W.
The video told us.
Changes our DNA.
Yeah.
Right? So it ionizes things. So if you put a lot of energy in, either in the form of light, or you literally throw an electron in, it can actually create ions in our body that then lead to chemical reactions. So nuclear reactions lead to chemical, and if you have chemical reactions happening in your nucleus of your cells, that can be really unideal. Any more? Okay, so our time for the semester is up. There are a couple practice problems on this worksheet. We have gotten as much through nuclear as I wanted. I want you to be more aware of what it is and how it can work. So